Gradient descent. In part 4 of neural networks, we'll see how to use gradient descent and what role it plays in neural networks and how it interacts with all the neurons. So let's get into it. Loss functions. What are loss functions? They're basically just used to compare neural network outputs to the actual value. And this must be an average value. We'll use these variables, y, to represent the true value of whatever it is we're predicting, and a to represent the neuron's prediction. And in terms of weights and biases, as seen before, z equals x times w plus b. And we pass z into an activation sigmoid of z equals a. Now, previously, I've referred to activation functions as f of z. Just replace the f with the sigmoid. It's just a cooler way of writing it. So a is just the value when z is passed into the activation function. We'll start with the quadratic cost function. Although this equation might look extremely complex, the understanding behind it is quite simple. All we do is calculate the difference between the real values, y of x, against the predicted values, a of x. Refer to a previous slide where we assign these as variables. The L that you see in the equation is simply denoting the last layer. And finally, we square all of this because it keeps everything positive and it punishes large errors since they get bigger when you square them. So all of this is representing is the difference between the predicted value and the actual value. These are the inputs of any loss function. W, so C is the quadratic cost function in the previous slide. W is the weights, B is the biases. S to the R is the input of a single training sample. E to the R is the desired output of that training sample, basically the real output. And W and B are encoded into A of X. Minimizing loss. Loss functions get really complex really fast, as you can see from the top left picture. But how do we minimize the loss? We want our neural networks to be as accurate as possible. We need to find what value of W, the weight, results in the minimum value of C of W. So C of W is portrayed by the graph in the bottom left. So how do we do that? We use gradient descent to find that minimum value of W. How do we use gradient descent? So all gradient descent does is calculate the slope at a point. Then it moves in the downward direction of the slope until it converges to 0, which indicates the minimum. So if you see on the top left, you see the slope is negative and it's going down and down and down. And then the picture at the bottom left shows when the slope is 0, which is where the minimum is. Learning rate. So learning rate is just the steps we take to find the minimum. A smaller step size takes a lot longer. If you see the picture in the middle, that's a small step size, which goes really tiny pieces of narrowing down the slope at a very small rate, which takes a lot longer to eventually get to 0. Larger steps are faster, but they risk overshooting the minimum. If you see the bottom left picture, that shows large steps, which are really huge. They drastically jump between slopes. And as you can see, it drastically overshooted to start increasing the slope instead of getting it to 0. The step size is called the learning rate. We could start with larger steps and go smaller as the slope gets closer to 0, which would be much more efficient, and that's called adaptive gradient descent. So if you can imagine it, it's starting with these large step sizes, but then getting smaller and smaller and smaller until you converge at that zero. Next, we'll discuss what cross-entropy is. For classification problems, we often use the cross-entropy loss function. This is similar to the quadratic cost function, but it's a little different. The formula for the cross-entropy function is shown on the left. Cross-entropy assumes that the model predicts a probability distribution P of y equals I for each class, 1, 2, 3, to some c. These are all of the classifications we want. It's also for binary classification, or you can use it for an m number of classes that's greater than 2. For example, you can use cross-entropy for assigning, I don't know, like a color of a shoe, whether you want black, blue, red, yellow, any color you want, and these would all be classes. In this case, we'd have 4 classes, so this is more than binary classification. This is the m number of classes. For binary classification, it would be like, did the person throw the ball or did they not? If you're talking about maybe a sports game, that would be just a yes or no question. So once we use this big formula to get our loss value, which is the minimum value of W, how do we update our weights and biases so that our model reduces the loss? Remember, a loss function simply says what is the difference between the model's output and the actual output. But once we have the difference, how do we change our weights and biases to actually reduce that difference? That's where backpropagation comes in, where we go backwards to adjust our weights and biases and tune our models to have a greater accuracy. So you'll learn about that in the next video, and I'll see you guys there.